Okay, good day and hello everyone to whoever is watching this video. So today I will be teaching you about the symmetry elements and operations of methane with the molecular formula of CH4. It has 1 carbon atoms and 4 hydrogen atoms attached to the carbon atoms. So in total there are 24 symmetry elements of methane, and let's go in one by one. Okay. So this is the molecule that I just made here. It is in a tetrahedral shape. Okay, the first one is C1, which is very easy. So basically C1, you just leave the molecule there without doing anything. So this does not bring any change towards its original shape or orientations. So the next one is C3. So I'll show you what does it mean by C3. Okay, so for C symmetry operations, it so in general formula is Cn is equal to the 360-degree full rotations divided by the n number of the C operation. So we have C3, so it's actually 360-degree divided by 3, which is 120-degree. So what does this actually mean? So let me show you to get a clearer view. Okay, so this is the original position of the CH4 molecule, right? So we rotate it 120-degree, like so. As you can see, it's back to the same shape as I originally showed you. Okay, but if you remember in the original paper that I showed you, I wrote that it has 4 C31 and 4 C32. So what does 4 C31 means? Okay, as you can see, if you take the view from one of the hydrogen atoms and rotate it by 120-degree, you are back to the original shape, right? So turn your attention towards any other hydrogen atoms. For example, this one right here. So again, undergo the same rotation, 120-degree. See, it does not bring any change to its shape, so it is an acceptable symmetry operations. So again, what about C32? So C32 actually means you are turning it 120-degree 2 times, which is 240-degree, right? So again, we put this here. The first is 120, the second one is also 120, in total 240. So just rotate it. First rotation, second rotation. Again, it does not bring any change to its shape, so it is an acceptable symmetry operations. And just like 4C31, turn your attention to any of the hydrogen atoms and you will get you will get 3 more C31, C32, right, and 4C31. Since there are 4 hydrogen atoms where you can turn your attention and do the same operations over and over again. You might ask, why don't we have 4C33? Well, C33 right here is basically 360-degree divided by 3 times 3, which is just 360-degree again, which is just C1 that I just showed you earlier, right? So next, we are moving on to the C2 symmetry operations. Okay, for C2 symmetry operations, there is actually an easier way to see the operation. First of all, draw a nice square on your paper or on the surface that you want to detect the symmetry operations, right? Okay, tilt it slightly so it is diagonal towards you, right? So now, hold your molecule so that two of the hydrogen atoms is placed on the corner of the diagonal square, like so, right? So here, you have to get C2, just like the initial formula, 360 divided by 2 is 180, right? So this is 180-degree. Turn it again, 180. See, it's back to its original shape. Now change it towards another pair of hydrogen atoms, like so. Okay. Also turn it 180 degrees. See, it's back to its original shape. So it is also an acceptable symmetry operations. The last one is here, right? So just do the same thing again, 180 degree. So there it is. That's how you can get three C2 symmetry operations. Okay. Next, I will show you how to get the sigma dihedral planes of reflections. We will use the same strategy as the C2 symmetry operations, which is first draw a square, tilt it slightly, and place the molecule so that two hydrogen atoms touch the diagonal corners of the square, like so, right? So just leave your molecule like this and get something long and thin, for example a ruler, and place it across the square, across the corners of the square. As you can see, it is dividing the molecules equally. Now, just like a square, if you have one side that is diagonal, you can also put it in the perpendicular direction, like so. It also dividing the molecule into two perfect parts, right? So just like the C2 here, which you can get 3 C2, this one is also the same. Just move around with the molecule so that you have two different pairs of hydrogen on these diagonal corners of the square that you draw. For example, like this, right? Again, do the same thing. Put a ruler over here and put a ruler over here. So you get two. And like C2, since you have three instances where you can put the molecule in the box to get different orientation, it is also applicable to the sigma dihedral rotations. And since one instances in the box can get you two planes of reflections, there are three instances, so you can just multiply. There are 3 times 2, so there are in total 6 sigma dihedral planes of reflections. So next I will go to the last one, which is a bit trickier, which is the S4 rotation, S4 operations. It is a little bit tricky since it involves both rotation and reflection. But again, we can also use the same formula or the same trick to get the sigma dihedral and the C2 operation, which is drawing a box and again tilt it slightly and put it in the corner. So S4 means the 360 divided by 4 get 90 degree, right? So just turn it 90 degree and then reflect it to the perpendicular axis that you just rotate. So since you rotate it here, the plane that you're going to be reflecting is right here, so just reflect it like that. See, you have the same shape as your original molecule. Okay, let's start from here again. So see, you start from here, you rotate it 90 degree, then reflect it, still the same molecule as earlier. So that's how you get S4. So in total there are also 6 S4, but again, like C2 and sigma dihedral, you have 3 instances where you can get different orientations. So that's why you get 3 S4. And S4, 3 S4 negative 1, it is the same thing but in the different directions. So that's all on how you can get all 24 symmetry elements and operations of a tetrahedral molecule. Thank you.